Ahmed's unicycle tire starts off at 22 degrees Celsius and 0.75 liters. If it reaches 0.72 liters, he needs to refill his tire. So, what temperature might Ahmed need to check his tires when the temperature drops and he has to refill his tire? So, we have to have two PV equals nRT equations set to each other, one that's initial, one that's final. So what we could do is divide by nRT on this side so that we can have PV over nRT. And then we can set this to a new PV equals nRT equation after the temperature drops. So let's look at what is constant and what is changing. Is our pressure changing? No, it's not. Is our volume changing? Yes, let's keep that. Is our moles changing? No, it's not. We're just looking at what happens when the temperature drops. Is our R constant constant? Yes, it is. It's a constant. So the only thing that's changing is our volume and our temperature. So we can rewrite this as volume initial over temperature initial equals to volume final over temperature final. Well, let's plug in our numbers. So we have our first volume initial is 0.75 liters over our temperature initial, which is 22 degrees Celsius, but we want this in Kelvin. So 22 plus 273 will give us our Kelvin, which is 295. So we got 295 Kelvin is equal to our final volume, which is 0.72, over that temperature final. So we don't know what that temperature is. So if we solve for temperature final, we get 283.2 Kelvin. Now if we wanted to write this in Celsius as well, we could. We could just have to subtract by 273, and this would give us 10.2 degrees Celsius. So these are equivalent. Now, suppose that cold weather does come upon Ahmed and his unicycle. So how many moles of air will you need to add to inflate from 0.72 liters to back to 0.75 so you can maintain that same pressure, assuming you already have 0.031 moles of air. So let's rewrite this. If we have a PV over an RT equation set to a new PV over an RT equation, let's delete what is constant. Is our pressure constant? Yes, that's what we're trying to maintain. Is our volume constant? No, we're changing that. Is our moles constant? No, we're also changing that. Is our R constant? Yes. Is our temperature constant? Well, we're saying that if we're already at 10 degrees Celsius, we're not changing temperature here. We're already assuming that it's already 10 degrees Celsius and we're trying to get that pressure back to where it's at. So our new equation is V initial, or initial volume, over our moles initial, is equal to our volume that's final over our moles final. Now, if you look, it says how many moles of air will he need to add. So we're looking at what our final is minus what our initial is will give us the moles added, right? This is the change in moles, essentially, is what we're trying to find. So keep that in mind when we solve this. So as we plug in our volume initial is 0.72 over our moles initial, which is 0.031, is equal to our volume final, which is 0.75, over our moles final, which is NF. Now, if we solve for moles final, we get 0.03229. So I'm going to keep that. Even though we only have two significant figures, I'm going to write all that because it's going to help us. Now that we have our final moles, let's find how many moles we actually had to add. So if we have NF, which is our moles final minus our moles initial, that will give us the moles added. So we have 0.03229 minus however many moles we started off with, right? This will give us 0.00129. Now that we only have two significant figures, we'll just round it to 0.0013 moles. You can also write this as 1.3 times 10 to the negative 3 moles. So that's how many moles of air he had to add in case the temperature actually did become cold.